Hello, my name is Marcus McGeary, and this is my PHYS1160 experiment results, and that's my student ID card. Alright, so the first part of the experiment which I did, which was the understanding the solar system, was describing Kepler's 3 laws. So the first law of planetary motion is, I have them written down over there, is that each planet orbits in an ellipse. So each planet orbits in a shape like that with 2 focuses, and the sun is always at 1 focus point. This is just a law that is followed by all planets in our solar system and the majority of planets everywhere else. Of course, there are some exceptions when a solar system might have 2 suns to orbit. Then at that point, it will be the focal point will be the center of mass of the 2 suns which are orbiting each other. I don't know whether you can see that. Okay, you can. Okay, great. So the second law of Kepler's planetary motion is that this imaginary line here, so if there's an imaginary line going from here to the focus point of the sun there, this area that is swept out in, say, an orbital period of t, this area here is proportional, or is exactly the same as the area swept out during the same amount of time on this side of the planet, or the orbital period, sorry. So this area here is always going to be the exact same as this area here, which just generalized means that for any orbital period time, the velocity of a planet would change depending on its distance to the sun, which is also Kepler's 3rd law, which is that the square, okay, I'll draw another diagram. So for the semi-major axis, which is this axis here, this distance squared is proportional to the orbital period of a planet. So basically, if a planet is extremely far out, let's say Pluto, or I guess Neptune, if a planet's far out like Neptune, it will have a much larger orbital period than a planet such as Mercury, which is much closer to the sun with a much smaller semi-major axis. So we proved that later on in the experiment, I think in one of the later questions. Oh, running out of time. So they wanted us to prove question 9. Question 9 asked us if the planet moves as the moon orbits. So of course the planet will move, but just not significantly. This is because obviously Newton's the first law of motion, F equals ma. Every action has an equal opposite reaction. If you're pulling on a planet with a gravitational force, it's obviously going to pull you, and you're going to spin around just a small amount, not a significant amount, but of course you will move. How is this different to the sun-planet scenarios above? Essentially, it is the exact same. The only difference being that for the sun scenario, it has a much larger mass, so the distance it's moving will be much smaller than the planet is moving for the sun-moon scenario. Where are the centers of mass in each scenario? So the center of mass for each scenario will be the same. Let's say we have here, and we have the planet here, or the sun and the planet here. The center of mass will be somewhere in between. A way to find this is to just equate the forces using the formula we get in PHYS1141, which is, so you equate the force acting here and the force acting here, and you get a distance somewhere in between. The only way this is different is for the scenario where there's no gravitational force. Instead of the center of mass moving in an orbit around this planet, around the sun like this, it will instead, so what happens is, instead of the planet orbiting around like this, it will instead move straight up because there's no gravity pulling it down, and then the center of mass of the system will just continually move upwards. Ooh, running out of time. So take a star in the standard configuration when the grid lines are turned on. What is the distance between the markings in AU? It's 1 on 2. Oh, okay, I ran out of time. Come on.